Okay. So the goal of this stream is to try and work with this Python library on zero knowledge proof. They okay. Oh, let's start. I don't know about this library, so basically I'm learning right now. Okay, getting started. Let's go. Okay. It's downloading. Let's try this example. So this is Peggy the prover. Peggy. Yeah, Peggy CD fan. ZK proof. And what happens when I do Python 3, Peggy the prover. Okay. Okay, so let's try to all right. So this is the challenge of Peggy. And what if I now what's the name of Victor? Victor the verifier. And so yeah, but I want also need to print the statement. Print statement. And what happens when I do Victor? Okay, it's not defined, and it needs that maybe. So I don't know why they didn't put it here. It is not defined. Okay, how that works? So are they supposed to be in the same file? Victor. Here you will see that better maybe. Okay. Okay. We have Victor and we have Peggy below. So what happens if I just copy everything from Victor and I put it here? So we have print. This is the Peggy part and this is the Victor part. So does the chat works? So let's see if this actually works. Let's do that. Bin user bin and Python 3. No. Oh, what's the file already? Yeah, Peggy. So chmod plus x Peggy. So if I do Peggy, all right. Okay. So we have, okay, if I understand that this is the challenge and this is the statement and it has to verify the statement via the proof. Okay. All right. Now I want to, okay, so this is, okay, basically, how does that? Peggy commits to a secret bit and wants Victor to prove in zero knowledge, etc. So this is an example. Okay, but what if I want to prove something else? Where is the documentation? Here it is. Okay, so privacy preserving, we propose Diversity provides an API to define concurrent notations. What's this? What's that? 8, where is 8? Here. Okay, okay. Efficient, extended abstract. Efficient group signature. For like this one. What's this? Notation introduction, blah blah blah. Group signature scheme, the concept of group signature. Group signature. Signature, those members. Oh, why that? title as in change, history, science and technology, programming, okay. Okay, so everything is cool here, everybody can listen to me. That's okay, the chat is working. Okay, I'm gonna have a photo here. I want to put a photo of mine. Okay, let's put some tag, search tag, blockchain, what if I do cryptography? There's no tag in cryptography, programming, blockchain. There's no tag blockchain. I think people don't like blockchain here. What should I put? Skincare? Lol. Okay. Okay. So let's go. Uh, so the goal here is to learn how to use this library. And in order to do this library, yeah, here is the GitHub page. Those are zero knowledge proofs. And zero knowledge proof is, I think, people that are watching do know what zero knowledge proof is, but if they do not know, zero knowledge proof, and you can go on Wikipedia, AG, cryptography, zero knowledge proof, in which one party, the prover, can prove to another party, the verifier, that they know a value x without conveying any information apart from the fact that they know the value x. So you can see some example here. Peggy randomly takes either part A or B of this path, but she doesn't tell Victor anything about it. In fact, Victor is waiting outside. So Victor chooses an exit, and once Peggy's in the path A, either A or B, then Victor will say, yeah, you should exit from the path A. And if Peggy can go outside the path A, then Victor can say, okay, yeah, you have the key for this gate. So basically, you You can't do that only one time because you can't do only one time, you can do only once because, yeah, maybe you chose the path A. Let's say that you chose the path B. So if Victor says, yeah, exit from path B, then Peggy can exit from path B without proving that she knows the key. But Victor, if Peggy and Victor play many times, they can do that. Okay, I think that there is nobody here. If you are here, please write something in the chat. Okay. So yeah, but basically they have those things, but what I do not understand is why this thing here, why there are problems. So they make this thing here. They are R the secret, but they don't have R, which is this R value here. Okay, so basically I have to put, they have secret here, the statement, but then he says, well, I don't know what you don't know, basically. You don't know ZK proof. So basically, if I want to do that, I should print the ZK proof in a file, and he should read it in order to prove those things. Okay, let's do that. Yeah, so I have two places and things are better. So let's do that. What the fuck? Okay, write on file, write file, F open, F write. Okay, let's call it zkproof.txt in a write mode. Okay, and we put zk proof here, and then okay, we do the same thing on the other thing where you basically have to read and this is zk proof So Victor reads the file with zk proof inside, but the file is not called demo file, but it is zk proof.txt. Okay. Assert print and we don't need those things, right? And finally, we want to chmod x Victor. So basically we run Peggy oh, but is there something like to string maybe? Let's do that from the command line. Okay, and if I do zk proof, deserialize oh, okay, zk proof. I wanted to have this variable as a string. So if I put challenge, oh, but what? Okay, so let's say I have zk proof here, which is this thing here. It has a challenge, it has a response, but what is a help? It said before that is not a nix. What's that? Must be string, not nix. Type of zk proof, zk base, okay, help. It's not defined. What's that? I imported everything from that. Okay, and what if I do base? Okay, not defined. Let's see the doc. Ah, okay. Okay, we have a good Core API. Okay, there is a way to pass these proofs from one place to another. But I need to understand what these nicks are. So if I do import zksk and then I do this thing here. Okay, now it's working. Okay, built-in subject, find serialize. So we have a big object, but how can I save a object to a file? So Python save object to file. Saving an object at a persistent company name value. Pickle. What's pickle? Import pickle. You could use modern installer libraries and every application. Yes. Okay. Port pickle company pickle as output. Okay, so there is a way to use to transport objects. Okay, so you have to use pickle. Well, we will do that in the future. So there are no follower here. Man. Okay. All right. So we are trying to understand how to use this library here to do zero knowledge proofs. And right now I am just trying the library to get a glimpse on how it works. So basically, so if I want to transport an object, I have to, how can I? Yeah, copy link. I say, print this is the vector part, and here is the way to transport the object, and this is the vector part. We decomment. What happens when, okay, we can exit from that. What happens when I do the, basically the whole, okay, there is this, what is right, okay. We don't need that anymore because we do not write any object on any file. So this is the statement that, okay, so this is the Peggy part. We should write those things better. So let's put a new line here. And let's put a new line here. Okay, this is Peggy part. And this is the Victor part. All right. Okay. So those are the things, yeah. But right now I have just proved how to, yeah, black on black is very cool. Okay, just proved how to do this thing here. So basically, they are proving that, where is the getting started? Basic one. Proving that given a bit r, either c is equal to rh or c minus g is equal to rh. So, wow. So, yeah, but Karmash Stedler, zero knowledge, we know this bit, but yeah, but how this will prove that he knows the bit? I mean, top secret bit times G plus R value. Okay, yeah, so this is the commitment. This here is the commitment. And why the proof works? Because, yeah, this is this top secret bit, which is 1 or 0 times G plus R value H. So I can ask you, well, commit to this R value, to this R value, and you put it this one. Okay. Ooh, okay, so if the secret bit is 1, then your proof will be this one, C, you will receive C, and if the top secret bit is 0, so C is equal to R value times H, while if the top secret bit is 1, then C minus G will be equal to RH. Okay, so we got the why this proof will prove that R is either 1 or 0. And if I can send you this proof, you basically are convinced that I know this secret. In the sense that, okay, now I understand. So you basically you have this top secret bit here, and you are good with a seed. And if I play many times this thing, I can prove it to you that I know this top secret bit, which is always the same. Peggy's definition of the proof statement: the first OR clause, so this one or that one, corresponds to the secret value 0, and the second to the value 1. Okay, so because the real value bit is 1, the clause that corresponds to 0 is marked as simulated. All right, so if I put 0 here, I have to put simulated here. Let's see if this thing works. Okay, it seems to work. But what if I put import random and we have z equal random dot range 100. import random, rand array is it equal to, okay. Okay, it's working. And so from random import rand range, I can say rand range 100. Let's see if this thing works. It's not working. All right. Okay. They have to. So we have rand range here, and this is in another rand. So this thing doesn't work. Okay. This has to be the same. This thing is equal to Z. All right, so this is working. So what if I say that the random bit is another one? Okay, assertion error. Yeah, because probably the proof is badly done, and so people okay, so it gives you an error. Put the right bit here. Okay, and this is how you commit to a value. Okay. You can do simulation. Simulate pre-commit. Okay. Basically, annotation and syntax. Defining. Okay, let's see. Computation analysis groups, inducibility curve. When we use mathematical expression, we write points on those groups. Okay. We follow the Python convention and write both groups and groups elements. Okay. For example, proof of knowledge, secret data. So how does work? Why is it here? Ah, it is the right one. No, it's not the right one. Let's prove a nominal solution for successful identifier with overwhelming probability. A cheater can't do that. Through the knowledge of the discrete logarithm epsilon equal g to the x or base g, the prover computes the following values. V is chosen at random. We have t equals to gv. C is an hash, right? What's h? What is h here? Oh yeah. Finally, let a collision-resistant hash function that maps binary representation of the argument to a binary string of length L. Okay, how can I exit from this moderator chat? So, okay, we have an example here to prove a knowledge of discrete logarithm of epsilon minus, this is a minus, equal to g. The base g, the prover computes the following values. So we have v, which is random. This is an hash function. And this is, okay, let's do another Peggy thing. We copy Peggy in Peggy 2, v Peggy 2. All right, we have another, I want to prove that I know the knowledge of the discrete logarithm epsilon of x. Okay, so first step, I create a random v, then I create this c here, and then r is equal to v minus cx. Current commitment, challenge and response. The resulting proof is the pair CR and okay, values called. Resulting proof is a pair, which is can be verified by everyone. The first breaker meeting. Okay, they do this thing, and they check the equation. Is C equal to this thing here? So the proof of knowledge is basically as a Schnorr signature of the message G. Y, which is cool. Yeah, yeah. Okay, I got it. Okay, let's implement this. Let's implement this shit. So I have to create this thing. Okay, insert Q. So this is the Peggy part. Let's say that Q is equal. Are there some things about Q that I have to know? Okay, Q can be everything I want, right? So Q is equal to, let's say, 100, and I have to create a random number V, which is in the range of Q. And then basically okay, so we have to create a base. Let's say that the base is equal to, but what's G here? Let's see, be finite. Okay, whatever I want. Oh, primality of Q. So let's say that Q is equal to 101. The necessary condition, the discrete logarithm of an element y in G is to the base of G, the unique integer. Right. Can I use, should I have to use some special cases are not allowed, or cannot present flawed proof, but it will try its best to detect issues. Reach two group points. Okay, but so basically this thing. Oh, Mac support is not guaranteed. Well, I am on a Mac. It is tested on Debian-based system. Well, we hope it works even in Mac-based system. So, what's the paper saying about this? Zero knowledge proof. How in this paper is presented what documented by the library. Yeah, but what we write using additive notation G and G. But yeah, but can I use every kind of G or H or? Okay, so okay, so they are basically all okay. So they are all non-interactive, right? Sigma protocols. Zero knowledge Sigma protocol on Sigma protocols. Zero knowledge proof is, let's see what they are, because there are interactive zero knowledge and non-interactive zero knowledge. If it is interactive, we have to communicate, while if it isn't interactive, then I just send you the proof and you can verify everything from it. Sigma protocol interface protocol for proving knowledge of some kind of relation. This post will talk a bit about Sigma protocol and describe an example. So this is basically taken from the paper, which we were seeing there before. What is that? This? Oh, I have a follower. Whisper, words, urban request, prediction. Yeah, but I don't want this view collapse. I have to learn how this thing works. What's that? Now I want to exit from this view. How can I exit from this view? Now the program verify engage in an interactive version to use a hash function such that you cannot predict the output of the hash function. If I don't try so we want to this version of it. The prover just generates a random number and creates a commitment t equal g to the r. So let's try. So we put g equals to 3, and as I understand that thing will be, so creates commitment t equal g to the v in my case, let's call it r. G to the r, yeah, but it is mod q. Then the prover hashes, let's call it, to get a challenge chi, he will hash, okay, so we import hash lib, and then we do a hash lib dot sha 256 of, oh yeah, but I need bytes. I need bytes. My dustbin doesn't tell me how many people are there. I want people. I want people. There is nobody here. I want people. Expand. Expand. Okay, so we have this thing here. Yeah, but I have to transform it. Python. Great. Let's say I have a number 46, 5, and I have 2 bytes. Okay, so I can say, let's say 32 bytes, big endian order, and this is, yeah, what, this is a very bad, but what if is there a way to have first 10,000 primes? Okay, list of prime numbers. Okay, let's take this number here. Really? So there is a page about number 700. LOL. Oh, there is a super prime. What's a super prime? Subsequent to occupy prime number position within the sequence. Ooh. Yeah, I like the super prime. We got a super prime. We got a super prime. All right. Yeah. So this is it. Okay. And if I do import hashlib and I say, let's say a plus a, Yeah, I got it. But if I say a byte is this, and if I say a byte plus a byte, I get this thing. All right, I like it. I like it. I like it. I like it. So I can do this thing here. Um, let's do this function. That's byte bytize bytize. Okay, like this. Of a number a is equal to return a dot to bytes. Is it written like that, right? Okay, to bytes 32 in big endian. Okay, so I have to return from the, where is the blog post here? G is equal to 3, y, okay, let's say that I want to x is equal to, I don't know, 23. And therefore, we have y, which is equal this thing here. Setup is wrong now. And he says, well, look, you should do an hash of g, quindi by ties g plus y, so by ties y and t, so by ties t. And print c. That makes sense. Digest print c dot x. All right, we have the x, the hash. Prover create a response to the challenge. Oh, there is a Python code demonstrating this protocol. Kubernetes curves. You really can't understand anything from that. Examine elaborate compilers, secure computation. We express the proof statement x equal. Oh, right. Okay. Okay. much is that I'm streaming? Well, 1 hour. I didn't do any new proof in 1 hour. But how does that the Twitch thing works when it says that there are 4 people in the chat, but there is only one person watching now? So I don't understand. How many people are there? What's that? Account creator today? No, 10 years ago, 10 days ago. I don't understand. So if you are in the chat, you can write in the chat. So this is basically the first stream I'm doing, so I will know more. So let's see. So if you want to implement this thing, you have to do those steps. Sigma protocol that proves knowledge of X such that secret group, okay. Okay, we call the discrete logarithm representation of C honest verifier zero knowledge Schnorr proof of identification. The prover sends a commitment, which is the value big R. Okay, so there is another notation here. The verifier sends the challenge C, and the prover sends the response SX. Finally, the verifier checks the correctness of the response. Every Sigma protocol follows the instructions. So let's change notation again. You have G, you have Rx, which, okay. Big R is this one. Okay. Then, okay, but Then make it easy to express a question about discrete logarithm. Listing one, show how to express the statement. Okay, all right, okay. First, the prover define the values which will prove knowledge, like, okay, all right, okay. Why is small r, not big R? Okay, now I got it. All right, okay. Mm-hmm. All right, we proved knowledge lines. All right, okay. So basically, we have to. Okay. So prover. The prover what have to do now? Prover has the x value secret. So people, if you do not understand what's happening here, you should write it in the chat. Secret statement. The L wrap. What does it mean? The L. Okay, we will see that. Okay. Later, C and x times g plus r times h and proof is equal to statement dot proof. Okay. Let's do that. Let's call it a schnorr and let's write it in it. It's wrong here, yeah, okay. And ch mod plus x schnorr, and let's work with schnorr. Name C is not defined. What the fuck? In the code says the commitment C. Yeah, but how can I commit to a value? Okay, first the prover provides the values which will prove knowledge, which is line 2 and 3. Okay. Values of which it will prove knowledge. That is the real values of the secrets. Okay, so the secret thing. Okay, let's see what a secret is. So here the problem is that you don't have C. Now let's print X is, and then let's print X, and we do the same thing with, we do the same thing with R. Let's see what's happened. Okay. Yeah, that begs the question, what is this hash here? Now let's see how Twitch works. So we have Twitch save stream with on demand auto save streams. Let's see download to change the most surefire way to guarantee. If you quickly about you can download a break start this process. Yes, there. Okay. Okay. So will it save this thing? Okay, well, I will upload it on YouTube, so. Okay. Anyway. So we have this secret here, and then we have C. C is the commitment, and C is equal to this thing, but we don't have neither G and H. Should I decide what G and H are? And if so, let's see how was Peggy, the test. Okay, G and H are okay, and then I create this thing here. But then again, I have R, the secret, which is a random value, which is cool. Okay, so the commitment will be something along the lines. All right, R dot value. Okay. So that's okay. So if I define, I don't know, uh, let's say, what? Let's say that G is equal to 20. No, 20 is not a good number. Let's say 2. And H is equal to 3. Okay. And then I say C, which is the commitment, is equal to G to the X value times H to the power of R. And to be sure of that, let's do it that way. And okay, okay. So G and H are. See, I don't understand. We have the commit here. Okay, DL rep. So you see, we have the statement, which is the L rep, so either C equal to RH. Okay, all right. Oh, no, I'm not understanding now. Okay, so G and H must be two random numbers, and I get that. It's okay. So we put it here. These are random numbers. We can get rid of it, and you basically have not that G, but this one and this one. And then, okay, so the notation, okay, now basically you are saying no, you don't have to do that because we have changing the notation here. And but is it doing a change of notation? Yeah, it's doing a change of notation. Okay, this is a change of notation. Okay, let's see. Does this thing work? Should I? Or was it the R the problem? Okay, it seems that it is working. Okay, so you basically have to write, all right, okay, x prime, why? Secret. I want to see this proof. I need to understand how those things are made. Okay, okay, okay. So there is a challenge, a response, an overcommitment, and a statement hash. Okay, so the hash is done by the library itself, and we don't have to do this thing ourselves. Okay. Now I am. So basically, this tree is trying to understand how to program zero knowledge proofs using this library here, zksk, and following this technical note with these examples. Okay. So now we are proving the so-called Schnorr proof of identity, and therefore, yeah, it's hard to be honest. To prove and verify the statement, this one, okay. Note that you are seeing that, but the notation here is additive notation, while here it is multiplicative notation. Okay, so we have printed the proof. The verifier has to do the thing written in there. Oh, I don't care. The verifier x prime, comma r prime, are both secrets, and the statement prime stmt prime is equal to drrep c x prime times g plus r prime prime times h. And then we have to assert that statement prime dot verify proof. Okay, but we also want to print it. Don't remember if we had. Okay, there is no. Okay, the proof is true. It seems that the proof is true. Okay, like that. Got it. It's okay. But now I want to create my proof. I don't want to copy proof of others. I want to create my proof. Okay, so we proved it. So basically, if we wanted to prove something here, all right, okay. It seems that I can also prove this thing here, an OR constructions. All right, the OR construction simulate the untrue disjunct while honestly proving the true disjunct. We provided the detailed protocol in figure 3 in the appendix, so let's try to do that. Figure 3 in the, here. Okay, common input, they both know the group G, the base, I think, yeah, the base G and Q. And they both know group elements G1, G2, X1, X2. So the prover has an input X such that X1, big X1 is equal to G1 to the X. So we have R1, which is a random number ZQ, and okay, so it's done. If I am not mistaken, okay, all right, okay, so let's prove that. We basically want to prove this thing here. So we have one X, and we have a disjunction here, and we have to prove that either x1 is equal to this one or x2 is equal to this one. Okay. So before we proved that C is equal to G to the X times H to the R, and this was the proof. And what if we want to just prove that C is equal to G to the X? Let's try to change this thing. I just want to prove that C is equal to x to x to g to the x. So we cancel this thing, we cancel this thing, and basically we don't need R anymore. And also the statement prime doesn't make any sense anymore, written like that, but just R. Okay, so it's true. Okay, yeah, well, we have R. We shouldn't have R anymore. Okay, no, I don't understand. Okay, x is equal to 20, and we have this challenge, and the proof then it's true. So, okay, it's working, it's working. But now we want to prove another thing. We want to prove that either we have either g1 to the x or g2 to the x. So we have to create g and h, we call it another way. Let's call it g1 and g2, which are true numbers created for that. We have the secret, and we prove what the secret is. And we have another commitment, which is, in this case, we want to prove x to the value of g. So we have this one here, which is the one which is true. And we know that when the true statement we have simulated equals to, okay, so Peggy's definition of the proof statement and proof generation. The first or clause to correspond to the secret value is 0, which is not what we have, so that must be simulated. So we have this one, and we put an OR here, and we want this one, which is G to the H, and because it is the wrong one, let's say, we have to put simulated equals true. And we have to prove this statement. Okay, and we basically have to call it statement prime here, and we have to change from x to x prime, and we do the same thing here. And we don't need this line anymore. And let's say, okay, now there is no h, but there is g1 and g2. Let's call it g and h right now. And it's true, yes. Okay, we proved that. All right, all right, all right, all right. I understand, I understand. So, okay. So we want to prove that, and we prove it. We proved it. We proved it because if you are in online, you can write if you are understanding what we are doing. We are trying to prove zero knowledge statements. Okay, and we proved this one here. We proved that one here without uh, without looking. This is the important thing. I'm understanding this library. Okay, defining and using primitive. Yeah, but we have proved that. Okay. So what is the next statement? The next, we can combine statement into conjunction or disjunction. Okay, we already do that. Include several useful primitives, the knowledge, proof of knowledge of BBS signature, inequality of discrete logarithms, and range proofs. Okay, all right. So basically, what's a BBS plus signature? BBS plus signature is let's see the paper. Okay, well, I don't like those things. I would like to I want to prove something. I want to prove these things with this discrete logarithm. I want to prove that either what I can prove. I can prove something here. Oh, there's a Sudoku here. I don't care. I don't care. I don't care. This is the paper. Okay. Okay, so if you are interested in this is the zero knowledge. Discrete log of a given value. Yeah, we already did. Hamilton, okay. I want to do things with discrete logarithms here. Let's say that I want to prove to you that I know the okay, let's say that I want to prove that given two bases and therefore two values, I want to prove to you that um, they both have the they both have the same secret, the same exponent. So we have the secret here, and I want to prove this commitment. What if I have two commitments though? Oh, I can put two commitments, G1, which has G, and I have C2, which has the value H. And so the statement is uh, C1 xg and this one be inside the word. Why doesn't? Oh, I have this thing here, and I have that C2 is equal to x times h. I copy this statement here, and now that is called prime, prime. Then I go to the x and I do the same thing, and I go to the x and I do the same thing. We cancel that. And it works. So what I proved it here in this last example, because now I am tired, this last example I proved to you that we can finally have uh, given two values, they both have the same exponent x. Okay, it's all folks. Thank you for watching